intersecting the western limb, and of course discussing their platinum element concentrations today. So very briefly, I'll just nomenclature in case everyone isn't familiar. So an orangeite is a type of ultramafic, ultrapotassic melt formed by low degree partial melting of the lithospheric mantle, and famously are kind of similar to rocks that can entrain and bring diamonds from the mantle to the crust. Here, just have a little snapshot of one of the IUGS classification systems for igneous rocks. Once we pass through the first two phases there, at phase 3, we have at the end ultramafic lamprifiers, orangeites, and kimberlites as rocks that contain over 90% of their volume in mafic minerals. They have an innate granular texture, which forms as a result of variable contribution of olivine and phlogopite macrocrysts and phenocrysts, and they generally contain primary magmatic carbonate. Okay, so yeah, this dike swarm has been observed in underground platinum operations that have been developed through the Rustenburg layered suite along the western limb of the Bushveld Complex, primarily observed south of the Planisburg complex, extending for at least 45 kilometers along strike, and composed of possibly hundreds of dikes that are kind of anastomose and segment along strike. The dominant strike of the swarm is west-northwest, east-southeast. However, you can see towards the south, and especially the southeastern portion of the swarm, the dikes have a more east-west trend, and this could represent a structural control of the Bushveld complex itself. So yeah, the swarm has a mean age of 144 million years. So in relation to the Bushveld complex, it's related to a completely different kind of tectonomagmatic event. It just so happens to be geographically related. And significantly, many other orangite dike swarms in South Africa that confined to this age generally trace along strike for less than 10 kilometers and only consist of a handful of dikes. And significantly, they are quite often exploited for diamonds. This time period is also very significant in the Cartwell Craton and the wider Gondwana at this time, as it coincides with the rifting of Africa and South America to form the South Atlantic Ocean. And the tectonomagmatic processes involved in this towards the early stages of the rifting, where we have incipient rifting, maybe some sort of early plume heat. These conditions would have been ideal for the formation of kind of low degree melting at the base of the lithospheric mantle. And we have a number of orangite occurrences across South Africa. In the northern part of the Cartwell Craton, surrounding Bushveld Complex, we have a number of occurrences, including those at Klipspringer and Swartruckens. But with the addition of this Bushveld swarm, it's for sure the extent of magmatism in this area was much greater than previously thought, and so may have some implications in terms of diamond potential in this area. So I'll very quickly just highlight some of the key petrological features of these rocks. We observe quite a wide range in textures, ranging between aphanitic and macrocrystic and some porphyritic varieties. On the right hand side, you have two thin section snaps here just to show sort of two end member textures of the dikes. The one on the left is a fairly typical aphanitic orangite composed of phlogopite microphenocrysts set amongst a ground mass of olivine or serpentine, more likely, phlogopite, CPX, barite, calcite, oxide, and some apatite. On the right hand side, we have a pretty textbook macrocrystic orangite, where we have these quite large, highly terpentinized and often well-rounded olivine macrocrysts that represent essentially they're xenocrysts, disaggregated from the lithospheric mantle. We do observe base metal sulfides in these rocks, and they're generally pyrite, but they are kind of pretty rare and very small and disseminated throughout the ground mass. And if they do occur as discrete grains, they're very rarely exceeding 50 microns in diameter. So very quickly, again, just highlight some of the key bulk rock geochemistry. Here we have a major element and a trace element plot. We have the Bushveld dikes from this study and the yellow diamonds there, plotted with comparison orangeites from Star and Swartruckens, and also comparison with some Cartwell kimberlites. And the plot on the left is really just to highlight the sort of ultramafic and ultrapotassic nature of these rocks. Similarly, on the right-hand side, we have a trace element plot. again, just shows the disparity between kind of typical cartvel orangeites and cartvel kimberlites, and also highlights just how enriched these rocks can be in incompatible trace elements such as barium. And yes, we have significant degree of overlap between our rocks and other cartvel kimberlites, and they form within the same time period. So yeah, like I mentioned before, potentially some interesting implications in terms of diamonds here. Again, just highlight quickly some radiogenic isotope compositions that we can use to help constrain the source of these rocks and also the petrogenesis. Again, clear separation between kimberlites and orangeites within the cartvel here, and the isotope systematics displayed by the orangeites be consistent with melts that are formed from low degree melting of an anciently enriched lithospheric mantle source. And of course, for the Bushveld dykes themselves, that source essentially would be below the Bushveld complex in the base of the lithospheric mantle. So moving on to some of the platinum group element concentrations in these rocks. Total PGE ranges between about 1 and 13, with a mean in the region of about 5 ppb. And we can see on the left-hand side this chondrite normalized plot where each individual dyke analysis is represented by the light grey line, and the mean of the swarm is represented by the light purple line. There's a sort of moderate degree of fractionation between the PGE, which is also reflected by palladium-iridium ratios of about 0.4 to 17. Ignoring just a few of the more sort of anomalously depleted and single enriched sample with respect to the IPGE, there's quite a high degree of coherency in terms of PGE systematics across the swarm. On the right-hand side, we have the means of other orangeites from cratons globally, and you can see that generally the Bushveld dykes seem to have a slight depletion in terms of the IPGE, kind of relatively average in terms of their platinum and palladium concentrations, and sit towards the bottom in terms of gold concentrations for orangeites globally. The Bushveld dykes seem to have quite a smooth PGE pattern, especially when compared to those the means of the Corellian orangeites and Bata orangeites. However, this could just be to do with the sample size. With for example, the Corellian orangeites are just free samples, so any kind of high anomalies are going to be weighted quite highly in the mean there, whereas we've got 27 samples, so it's kind of quite smooth. Compared to other cartvel orangeites, the Bushveld dykes seem to have quite significantly lower, unanimously lower PGE concentrations. However, it's been noted in the literature a few times that these analyses for these cartvel orangeites, which were taken almost 30 years ago, the methods then might have been slightly over-exaggerating the PGE concentrations. However, the subparallel nature between the profiles of the Bushveld orangeites and the other cartvel orangeite data may just reflect something that's systematic of the cartvel craton itself. Again, just have a couple of biplots here just to show the variation in PGE. We also have a comparison, some morgul lavas and prototype xenoliths, and essentially this just serves to show that while they don't contain huge amounts of PGE per element, the amount they do have is higher than you'd expect for rocks that are formed from really significantly low degrees of partial melting, especially compared to basalts. So how do we account for this? If there's such low degrees of partial melting, we wouldn't necessarily be exhausting all the sulfide in the source. So how are we imparting a PGE signature into these melts? It's been suggested a number of times in the literature that the source of the PGE signature, and especially the iridium, could be related to the lithospheric mantle. We know that we entrain variable volumes of lithospheric mantle in these rocks, and so yeah, it's possible that there could be sulfide inclusions within olivine. We're entraining the olivine in the melt, and the olivine's partially melting and releasing the sulfide in order to increase the iridium concentration in the melt, or perhaps it's a more potent source from, for example, a polyphon chromatite. However, with the Bushveld orangeites, we observe dykes such as this one here, which are this is a really nice banded aphanitic variety, and it's clear that there isn't a large mantle component in terms of like xenocrystic mantle component in this rock. It's it's aphanitic, doesn't contain olivine macrocrystal. It's probably a slightly more evolved variety of orangite, but it has a PGE signature like this, with the really highly enriched, relatively speaking, in terms of the IPGE. In fact, I think this is the highest iridium and osmium concentrations observed in the dykes. So if the source of the PGE signature is disaggregated cratonic mantle, then how do we account for samples like this that contain really high IPGE and no observable sort of xenocrystic component? There's been a number of sort of suggestions for how these things can occur in rocks like this. So of course we could be partially melting the source enough to maybe partition a small amount of platinum palladium into the melt. That would this account for the sometimes 1 ppb levels of iridium that we observe in the bulk rock PGE signature in these dykes. Perhaps the moderate fractionation observed in the PGE signatures is related to fractionation of olivine. However, unlike the ultramagnetic amplifiers that Wang et al. Analyzed in China, there is no strong nickel and iridium trend in these rocks, so there doesn't seem to be a control from olivine on the iridium concentrations. We do see physical entrainment of cratonic mantle, so maybe in some rocks this does have an influence, but of course for the more aphanitic samples, probably not. Perhaps, of course, we do have some influence from a more potent xenocryst that could have contaminated the melt. Perhaps some more interesting things are happening in the source of these rocks. Perhaps we're having sulfide entrainment of sulfide liquid, or at these deep lithospheric mantle zones, maybe more sort of alternate methods are occurring in terms of imparting a PGE signature into melts. Maybe there's a degree of aid from carbonate in the mantle that's kind of helping transport these sulfides from mantle to crust, and maybe in these kind of highly metasomatized and often quite oxidizing zones in the lithospheric mantle, perhaps the PGE are just more accessible to melting, to the melts. It's don't have the answer to these questions yet, but it's what we're working on at the moment. And so just to quickly summarize, we've got this major swarm of orangite dykes in the western limb of the Bushveld, hundreds of dykes over a really vast area, much more significant, at least in terms of their size and volume compared to other orangite dykes, of which these do share kind of isotope and bulk rock geochemistry with. So if they're forming at the same time and have similar geochemistry, perhaps a diamond potential here. For rocks that are formed from such low degrees of partial melting, perhaps the palladium and iridium is lower than expected, and so maybe there's something at play in terms of incorporating PGE into these melts that is different from just the traditional partial melting models that have kind of been known for a long time.